Divergence. Consider a surface S in a vector field. To find the flux through this surface, we divide the surface into a small region of area ds. Then the flux through this ds area d phi is given by f dot ds, where ds is the area vector which is normal to the surface. Therefore, the total flux through the surface S phi equal to surface integral S f dot ds. If f represents the flow velocity of a liquid, and if the water flowing out of the volume is more than that entering in it, then the net flux is positive and indicates that there is a source of water within the volume. And if the water flowing out of the volume is less than that entering in, then the net flux is negative and indicates the existence of sink within the volume. Net flux will be zero if same amount of water enters and leaves the volume. Therefore, divergence or net flux gives an indication of existence of source or sink within the volume enclosed by S. Mathematical meaning: div F is the net outward flux of the vector F per unit volume as the volume shrinks to zero. That is, div F is limit delta V turns to zero, surface integral F dot ds divided by delta V. Physical interpretation of divergence. Divergence is a vector operator that produces a scalar field, giving the quantity of a vector field source at each point. It can be positive, negative, or zero. If more flux go out than coming in, then it is positive divergence. If more flux come in, then it is called negative divergence. If same amount of flux enter and leave, it's called zero divergence. How to compute divergence? Divergence of a vector field is given by del dot f, where del operator is given by dou by dou xi plus dou by dou yj plus dou by dou zk, and the vector f is given by fxi plus fyj plus fzk. So when you take the dot product, we get dou by dou x of fx plus dou by dou y of fy plus dou by dou z of fz. Divergence is a scalar quantity and may vary from place to place. Gauss divergence theorem. The theorem states that the volume integral of the divergence of a vector field over any volume is equal to the surface integral of that field taken over the surface enclosing the volume. Mathematically, we can write volume integral del dot f dv is equal to surface integral closed path f dot ds. To calculate flux through the entire volume, the volume is divided into elementary cells. We now calculate flux through a cell and add to get the total flux. Flux through a cell is given by the following figure. There may be cells which share common boundary and there may be cells which do not share common boundary. For cells which share common boundary, the flux through that phase cancel. For cells which do not share a common boundary, the flux remain. Therefore, for cells on the surface, the flux do not cancel. That is, volume integral reduced to surface integral. That is, volume integral del dot f dv is equal to surface integral closed path f dot ds.